flashing, so that's good. And I'm going to go to the document camera and we'll see how it works. And we'll hold our breath. We got document camera here, but not on the screen there. You guys see document camera. There we go. We got document camera here. Okay. So I have this little gizmo. Okay, this is a new little gizmo. It's actually pretty slick. Since you guys have all been through Physics 1, you know we have various pieces of equipment through the vernier system that allows us to record a variety of things. This happens to be a little gizmo that Macmillan has put together, and a lot of those same sensors are in this little box. What's nice about this box is along this axis of my box is the y-axis, along this axis of my box is the x-axis, and it has an accelerometer on it, and so it'll allow us to measure force. So where we're starting today is we're going back to Hooke's law. And remember, Hooke's law was related to springs. So I have a spring here, and we're going to actually do this. Unfortunately, I can't do a split screen, so I'm going to show you what I'm going to do. And I'm going to take my little box, and this is my unstretched spring, right? That's my unstretched spring, and I'm going to go ahead and I'm going to stretch. I'm going to hold my spring steady, and then I'm going to pull on the box, okay? So that's what I'm going to do when I collect the data, because we're going to look at the spring stretch, and we're going to go back and look at Hooke's law. So that's what I'm about to do. I'm going to switch to the computer here, and the computer's got the application, hopefully. We'll see. All right, looks like you guys are getting it, and it's being patient over here. So I have the application for my little gizmo box, just like we do with Logger Pro, and we're going to look at force versus position. So I'm going to go here because we're actually going to collect some other data. The wheel position are the wheels on the box, and then I've got force and I've got position, and I have the acceleration on there as well. So I'm going to hit reset because I'm going to do the fudge. So we get there, makes it nice, and it's going to think about it. Must have turned itself off. So now we're back to everything there. Okay, I've got it sort of set up. Yay. I'm going to hit the record. So in this case, I'm going to fix my spring, and I'm going to stretch my spring. So we've got a position where I've got a force versus position. I have not reset the data at all, but you can see where it kind of kicked in, right? So I'm going to do a force. Okay, I want to swap axis because I want force on the y-axis, and I want position on the x-axis, and I get a force versus position. And I'm going to come in here, and I'm going to look at the data from about here and through there. So if we remember Hooke's law said that force was proportional to the stretch in the spring, right? And the stretch in the spring was looking at what my original spring was versus my other part there. And that it also said that the slope of that line, whatever the slope of that line, was going to be equal to the spring constant. Now remember, we threw in a negative sign in there because it was a restoring force. Okay? So it was a restoring force. So we just did a Hooke's law experiment. And we did it in the classroom. So you guys can actually see it. And we can actually go ahead and calculate the slope of this line. So let's go here. So at our position of 0.02, we have a y. I'm going to write that down. It's going to be fun. Okay. So I've got the y-axis is 0.85 newtons at a position of what we had as a minus 0.02. And then over here at 0.04. And we had X is, or Y is 1.4 newtons. So I'm going to switch back to the document camera, and we're actually going to do that calculation. See if things work. And the time delay, though, is allowing for you guys to catch up on minutes, so it's forcing me to go slower. Totally forcing me to go slower. So we had our straight line, and we had a force. So this side was force, and this side was position. So my slope was going to be my change in force divided by my change in position. And my change in force was 1.4 newtons minus 0.85 newtons divided by 0.04 minus a minus 0.02 to get our actual change in position. Gives me 0.55 newtons on the top. Gives me 0.06 meters on the bottom. And it gives me 9.2 Newton meters, and that's going to be my spring constant. Now, since this is a spring that's out of a laboratory kit, that number looks relatively reasonable. Because most of the time we're looking and dealing with these laboratory kits of having a spring with a spring constant of about 10 Newton meters. So that gives us our spring constant that we're looking at. So just to kind of refresh what we're talking about here is when I had my spring, we used this being an x sub 0, that's our initial stretch, right? And we looked at our change from x sub 0 to a new x, and Hooke's law said that the force was equal to a minus kx, where this is the stretch. And the stretch was going to be our new position minus the unstretched spring. The negative came from a restoring force, and this was Hooke's law. And we also talked to you about how physics lies about everything, right? You know, we all lie about everything because rubber bands don't follow Hooke's law, right? And I think you guys actually did you guys do a Hooke's law experiment in lab last semester? I think so. I think you guys did a Hooke's law experiment. And what you found was initially I could add a whole lot of weight on this essentially it's a sort of a spring, but I could add a whole lot of weight onto the rubber band and nothing would happen. But once I finally hit a point and I hit that point where it stretched, my rubber band would actually stretch, and it actually had a period in there that would follow Hooke's law, which is why we end up calling it Hooke's law, because most materials are going to have a region where they're going to follow Hooke's law nicely. And eventually they'll have a region where they're going to deform, and then there are regions where it doesn't behave at all. But Hooke's law allows us to do that. And we could go back and look at force, because if I did the Hooke's law experiment, because I added a weight here, the force for that stretch usually was related to mg, and we could actually calculate it. So if I told you you had a spring that stretched a certain amount when we placed a weight on it, then you would be able to calculate the spring constant. So we get that spring constant, and if spring constants are usually in Newton meters, and just to refresh everybody, since we all had a break, right? A Newton is a kilogram meter per second squared. So a Newton meter ends up in some funky units. We end up in kilograms per second squared. But because of what we're trying to do, we usually leave the units in as Newton meters. So hopefully all of this stuff is stuff we've seen before and stuff you've had before. And we've looked at it before. And what's nice is now if I go back here to the desktop computer, right? What's nice about this, thinking about it. Okay, you guys got it over there. We got it over here. Whew. I wonder why the delay is on this side. That's kind of funny. But we got the nice Hooke's law behavior, a nice straight line Hooke's law behavior. We can calculate the spring constant, and remember that negative in Hooke's law is about a restoring force. All right. So I'm going to go back to the document camera again because I'm going to be able to show it a little bit better. And we actually did this demonstration a little bit on Monday. Okay, so I'm going to turn that up so it's white. So what we said on Monday is we're going to do simple harmonic motions. I got my gizmo down here, which is now a weight on the end of my spring, and we said with simple harmonic motion that if I push that weight on there, I can get this bouncing up and down, right? And we actually showed it on the screen about that bouncing up and down, at least in terms of force, on Wednesday. So I'm fixing to do this, because I'm always fixing to do things, right? Fixing to do things. So I'm going to go back to the desktop computer. We're going to collect some more data. We're actually going to do it. I'm going to hit reset. Thinking about it. Oh, it turned itself off again. All right. So I've got my force and I have my wheel position. I'm going back to my single graphs. And I'm going to actually set it in motion, simple harmonic motion. I'm going to start to record it. So we're going to let it go here. I'm going to record. Okay, so we've got some data. I hope we have some data. Because it doesn't really look like on that position data that we've got position data, but I'm going to hit there and I'm going to hit auto scale because it's actually going through a 2 meter section here. So if I go through here and I'm going to, so we are, let's go up here. All right. I'm going to do 0.5, number lock 0.5 to minus 0.5, see if we got data. Okay. That should be my position. We got the nice up and down there. And I'm going to try it again. Actually, I'm going to get rid of that. We're just going to do this, because that's all I need for right now. Okay, I'm going to make sure we're on. We're on. I'm going to hit, I'm going to bounce in here. I know what's going on. I have to do it a different way. Because I'm going off the wheel, not the other part. So we'll do it again. So hopefully, I'm going to do it horizontally across the desk. So I'm going to hit record. Oh, it's not going to let me do simple harmonic motion. Let's see. Oh, I know what I can do. We'll try it. I wonder if I can do it on the wall. Oh yeah, that'll work. Not nice and smooth. Let's see if we get some data. Let's see what happens here. Well, we didn't get some really nice and smooth data. That's kind of a bummer. I'm going to try the smooth side over here on the wall. I'm going to need you to help me. Can you try to help me? Yeah. Okay, I'm just going to hold the screen. Okay, got the screen on this. Yeah. Bummer. Thanks. Didn't work, but that's okay. Yeah, I'm gonna have to figure out how we're gonna get a position, but you guys have got the idea at least of what we're trying to do. So I'm gonna go back to the document camera and where we're at. Hopefully, I'm gonna use a grid paper. So I've got a grid paper, but we know what's gonna happen and what we've actually witnessed when it bounces up and down. If I do a position and I have a line like this, what we end up with is a curve that's going to go like this. And what we said on Monday, or Wednesday, what we said on Wednesday is that this could be a sine wave or it could be a cosine wave. And because of our lovely challenges that we had on Wednesday, I didn't actually drop into it as exactly what we were looking at, other than the fact that the difference between a sine wave and a cosine wave is what we call a phase angle. So if you go back and you look at your appendix in your book, sine of 90 degrees minus the angle is going to equal cosine of the angle. And that's a trig identity. And cosine 90 degrees minus the angle is going to equal sine of the angle. And if I'm dealing in radians, remember that 90 degrees is equal to pi over 2. Okay? So I could actually write those two trig identities either way. I could write it as 90 degrees, or I could write it as that one. Also, similarly, you can do that cosine of the angle is equal to sine of the angle plus 90 degrees. That's another way to write it. So depending on which book you get, is going to write that trig identity slightly differently. We're going to see those trig identities over and over again, and that's going to come into play as we move throughout the semester, so we can actually get a variety of trig identities from what we're doing. So we can utilize that. So I'm going to clean up my slide here, and you can find those trig identities in the appendix of your text. So, but basically what happens is, so I've got my chart here, and I'm going to do 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I'm going to start here, and I'm going to try and draw a really nice sine wave. Okay. And right now, this is a position versus time graph. Because we're not in statics, everything is moving with respect to motion, and I have a position versus time graph. Hang on, I'm going to turn things off here. So I've got that turned off. So I've got my position versus time graph, and if I look at cosine of 0, or sine of 0, so you go, just so you know where we are, and I'm going to be in degrees. Cosine of 0 is 1, sine of 0 is 0. The thing about sine and cosine, remember that the maximum that cosine can be is 1, the maximum that sine can be is 1. So what I've actually drawn here at t is equal to 0, I've got a value of essentially 1, because I haven't put any units on my graph yet. This is essentially a cosine. So this is a cosine. I'm going to put just a little a, and I'm going to put a t here, and that's equal to essentially 1. If this is 1, I'm about to erase that because I don't want it to be 1. So this could be any constant times time, and at time as t is equal to 0, that's going to be 1. So what I've drawn is a cosine curve. And I've done it now by putting a time component in there. So what you've had in math class was, well, I'm at 0. And so if I'm at 0, I'm at 1. But now I've said g, where that is related to that position. Now if I write cosine, I'm going to put just a little a, we don't know what a is yet, times time, plus a phase angle. This is going to define our start point. Okay? I don't necessarily have to start at 1. I could be, here's time t is equal to 0 right here. I could be at that point, and that would be all right. But how I'm going to tell where I'm starting on that curve is by putting in a phase angle. And that just tells me where I start. So doing something like this, this is going to define where I start. If I start at 0 and I have it all nice and pretty like I have here in real life, I'm at 1. So that's where we actually get to start. Okay, so that's looking at the function with respect to what we see physically of the bouncing of our particular item. So instead of 1, let's change that. Let's make this 5, because I did 5 blocks and I did a -5, all right? So I'm at 5. So if I do that, right now, my position as a function of time, has now been defined as the amplitude, A, how big this is, and so by definition, this is going to be amplitude. So strictly by definition, that's going to be amplitude. And we've got our cosine function. And now I'm going to go ahead and put in what we're going to be using, just because we know that that could be any constant, but I'm actually going to put in omega. And remember from last semester, omega is equal to my angular frequency, and it's equal to 2 pi times the frequency. Okay? So omega is my angular frequency, and 2 pi, and I'll show you the link to this here in just a minute. But we're going to put omega in there. We have time plus where we start. Now, because of this one, that just happens to equal 0 because we're starting at a nice spot. But this is going to be our general equation for our simple harmonic motion as a position versus time graph. Now usually we use Why? Because we're usually bouncing up and down like this, right? That's what we were trying to show with my little gizmo, that we're bouncing up and down like that. But that really is our angular, our angular motion part. So, things to look at and to know by definition. So, a likely quiz question that you might get next Friday is, on this graph, identify the amplitude. Well, the amplitude on this graph is 5 because that's how we defined it. Identify, and the amplitude goes from my 0 point to the top, so this is my peak up here, and this is my coming down here. So, but my amplitude has a magnitude of 5. This right here, so the time, and we're going to go ahead and give ourselves some units here. Let's say that that's 1 and that's 2, and this is in seconds. The distance between here and here, no, that's not going to work. I want to go from here to here. So this is going to be 3 seconds. If I drew it nice and neat. So from the same point on the curve, that is a period. Okay? That's my period. The time that it takes, the period is the time that it takes to make one complete cycle. And a complete cycle is the same point on the curve no matter where I am on the curve. Okay? So from here to here is a complete cycle. From this spot to that spot is a complete cycle. And remember that the frequency is equal to 1 over the period. So if we said that this is 3 seconds, the period is equal to 3 seconds. The frequency is now 1 over 3 seconds, or inverse seconds, which is 0.33 hertz. Just by looking at my graph, I have the amplitude, I have the frequency. And if I have the frequency, I can write that this is 2 pi times my 0.33, and this is going to be 0.66 pi. I can rewrite my wave equation, or my position, my function. So the position versus time is going to equal 5 cosine 0.66 pi time, and because we started at 0, the phase angle was 0, I now have an equation of motion. For my simple harmonic oscillator. So I've written an equation of motion for that simple harmonic oscillator that was bouncing up and down that could be represented by this cosine curve. Now when you guys do your lab, you're going to start off the labs with simple harmonic motion. Did you guys ever hear and talk, or Ina do it? Yeah. We used, instead of the sine or cosine function, the lab actually used the sine function. You could use it either way, but our book is going to start out with the position being cosine. Okay? So our book actually is going to use that cosine. The lab uses the sine. You guys over in Tonkawa haven't done the lab yet, but we will actually use the sine. And so it goes, you can use either one, but by convention in this text, we're going to use cosine. Now that's also important because if you pick up another physics textbook, they may use the sine wave, or the sine function instead of the cosine function, but the difference, remember, relates back to that phase angle. We can get back to that phase angle either way. So, let's look at this again. So if I give you a different one, so let's say that I'm going to go ahead and just change my axes here. Alright, change my axes. Instead of 5 is 0.5 seconds. So this is 1 second, and this is 1.5 seconds. This is going to be 3, and that's going to be 3. I can write the wave equation for this one. My position versus time is going to equal 3 cosine, which is going to be omega t. We still don't have a phase angle for this one. We've got to figure out omega. Omega is going to be 2 pi times the frequency. Frequency, the period ends up being 1.5 seconds. The frequency ends up being 1 over 1.5, which when I put that into the calculator, gives me 0.667. So now if I put in my 2 pi, my 0.667, this is going to be 1.33 pi. So now this is going to equal 3 cosine 1.33 times the time, and that's the equation for that line. That's the equation for the line. And I can do the inverse of that, right? I can do the inverse of that. I can give you an equation so there's an equation. I can ask you the amplitude. I can ask you the period. I can ask you the frequency. Okay. Amplitude is going to be what? 27. Now I'm going to have to do some calculations to figure out frequency, right? Because we know that the angular frequency is going to be 64. But that's equal to 2 pi times the frequency. So the frequency is going to be 64 divided by 2 pi. And so if I do that, plug that into the calculator, I get 10.2, the 3 significant figures. And that's going to be in hertz. So my frequency is 10.2. My period then is 1 over 10.2. And that equals 0.098. So if I give you this, you can pull out a lot of physical information from the wave equation that I just gave you. So you can go backwards and forwards to get us there. Okay? So let's kind of look at this a little bit differently because we've said that this is angular frequency, all right? We've said that that's angular frequency. So let me get somewhere real quick. That's one thing I didn't set up today, but we'll get there. And while I'm doing that, I'm going to come back over here. Since we're going to have a time delay, I'm going to have to get used to it. And a reminder, just so that you guys remember, that campuses are closed on Monday. We actually get a long weekend. Yay! It doesn't affect you guys too much because we're on Wednesday, Friday class, but you know, my other classes it will affect. Oh, since this is bright and early on a Friday morning that none of us wanted to get out of bed because it was raining and cold and ooky, and it's that ooky cold, you know, it's ooky cold. I am going to show you something out of one of my other classes, and I'm going to actually go ahead and copy it over for you because there was something that came out over break. And I will go ahead and show it to you. Okay, this right here, I don't know if anybody listens to, his last name is Gupta, and he does periodic reporting about psychology topics and how our brain affects our lives and things like that. And so this was an NPR story over the break, talking about does the way you feel shape what you think about your life. And even though that title of the talk or the story sounds a little interesting, it actually was doing studies based on picking your major based on what time you have a class. So if you're in a 7:30 a.m. class and you're tired and you're grumpy and all of that, it actually influences your opinion of that course material and actually can change what your major would be. So it's a kind of an interesting one. I encourage you to listen to it. I'm going to copy it over so that you guys have a copy of it, because it does happen to be, and I just see the life in this room this morning. It's just, the life over there. I just am seeing that. I'm going, okay, you guys are just, it's, okay, there we are. General Physics 2. So I'm going to let you guys have it so that you guys can look at it, because it really does, in fact, impact. And for all of you on both sides, how many of you got up before 6 o'clock this morning? I got one. Okay. How many of you got up before 7? I got a couple. All right. I got up at 5 a.m. to get here. So I'm already 3 hours into my day. So just kind of a thought process in there. And now I'm going to ask the other question. How many of you ate breakfast? I got one. I got a couple. I'm telling you guys, eating breakfast does help. It does help. So all those little psychological things just to keep us going. So it's a good piece to listen to, and in there. So you will find it now in the resource items. I have added it down there so that you guys can listen to it, so that you know what's happening. Okay. Over in here in the resource items, there is a simulation that you can play with Hooke's Law, so that you actually can play with it. There's the pendulum out there. Here's a YouTube simulation of simple harmonic motion. And here are some older lectures on the simple harmonic motion, so that you guys have those to play with. But what I wanted to come here is this right here, okay? This is a simple harmonic motion animation that shows you how you can look at that bouncing of the mass, which we've seen and we've demonstrated that it's going to give you that sine wave associated with it, and the traveling of a bead around a circle. And if we take that bead as a unit circle, and you could have it out on a chart recorder, and you look at the Y position with respect to time on that circle as it goes from 1 to -1 and back to 1. Or you can look at it in the X position, and it's also going from 1 to -1 and back of it. You can see that it really describes the motion of the particle going around the circle. And so we know that gives us our angular velocity, or our angular frequency. So that omega we've talked as angular velocity, we've talked about it as angular frequency. We know that we can get it to move and deal with it back and forth and be able to see it. So we can relate it back to circular motion, which is why I like to do waves after I get through my circular motion. And we talked about it, and when I mentioned it, I said we're going to see this again when we talked about the rotation. So you can really see, and they call it phase space, but we are going around that circle so we can relate it back. Also, here is a resource for you. It's a PDF, and it goes through the circular motion, and it's going to give you our spring, and it's going to define it with our restorative force. And this also gives it to you with the calculus. You guys don't have to worry about that, but it does get you the calculus back and forth. But here's our omega. But the mathematics and that's where I'm going to get to, the mathematics actually gives us that angular frequency is related back to two physical quantities of the system. If I have that spring weight system, it's easy to see. That angular frequency is going to be related to the square root of the spring constant divided by the mass. Let me say that again. The angular frequency is going to be related to the square root of the spring constant divided by the mass. Now it's easy to see when we're dealing with a mass that's bouncing on a spring. Because we know that that's a physical spring, right? We know that physical spring has a spring constant that's defined by the characteristics of the spring, and we know the mass that's sitting off the bottom of it. It's bouncing up and down. We know that. We've had that. We see it. We know it. Now the interesting thing is when you guys start to go on into doing other things. So let's think about this for a second. If I'm going to be in medicine and I am going to use radiation to eliminate a tumor, okay? Let's think about our microwave oven. Our microwave oven is tuned to a specific frequency, right? We know that because we've been told that and we've played with how does a microwave oven work. It's tuned to a specific frequency, and that specific frequency is the vibration, one of the vibration modes in a water molecule. So how we're going to heat up our food is we're going to get the water molecule excited because we're going to put energy into a vibration. Think of a vibration. If I'm doing a bouncing spring up and down, that looks an awful lot like a vibration. So what we're going to do is we're going to use a resonant frequency to cause that vibration to go like crazy, which is going to create friction, which is going to heat up my food. But now I can look at that water molecule as an example of simple harmonic motion and use that as a model. So we can model a lot of other things by looking at spring mass systems, solids for example, and looking at bonds as a spring mass system. We can actually really use that, and we can explain a lot of different things when we do that. And we can relate it back to some physical quantities. We can relate it back to that angular frequency that relates back to something physical, and we can use the simple harmonic motion to really describe a lot of different behavior. And so you've got this, and then again it gives you, but now if I look at my circle, okay, so I'm going to look at my circle. Look at how my point is defined by the x and y coordinate. My point is defined by that x and y coordinate. So as I'm going around, at this point, y is equal to 1. At this point, y is equal to 0. At this point, y is equal to minus 1. At this point, y is equal to 0. If I'm in a unit circle. Now, put that amplitude onto it, and now it's how big is my circle. Same thing for the x-axis. We can look at it the same way for the x-axis. So the mathematics is really going to give us some information, and we can use this later on in our other endeavors in order to be able to explain things that are in vibrations and looking at different pieces. So I've given you that particular aspect to it. So you've got that, and we've looked at it. This also shows you the phase shift. This little document shows you the phase shift. So you've got a whole lot of things that are in there, and we're about to dive into this thing about the conservation of energy in springs. So guys with me? Questions? Guys over there okay? Over at Tonkawa? Is this making sense? I've got a few nods. I'm not getting blank stares, at least. I'm not getting blank stares. So we're going to go back to the back of the camera, we think. We hope. Okay? We hope. Alright. Okay, so a couple other things that may be helpful that we may be seeing again. I'm going to change color. Another trig identity that may be helpful down the road is if I do the sine of an angle plus or minus another angle, that can be rewritten as the sine of the angle sine, no, I was right the first time, sorry. This is going to be cosine beta, and this is plus or minus. So if this is plus and minus, if I've got the plus, I use the plus. If I have the minus, I use the minus. That's a trig identity. And then if I have cosine alpha plus minus beta, this is going to equal cosine alpha cosine beta. And this is now a minus plus. So if I have a plus, that has to be minus. If I have a minus, that has to be plus. These are two other useful trig identities that you might have. Okay? All right. So, if we have a position, right? If we have position, so I have a position versus time, and that's going to give me a cosine, and for simplicity, I'm going to leave out the phase angle right now. We know that the velocity with respect to time is going to be my change in position with respect to time. Okay, now, I'm going to just give it to you. You can go through all the gory math to get there. But if I do that, and because I'm using my trig identities and I'm using those things, what happens here is this becomes a negative sign. My amplitude, my angular frequency, sine omega t. Okay? If you're in my engineering physics class, or you actually sit there and look at that document that we just kind of went through, you'll see that it's easy to get there through the calculus. It's much more tedious to get there through the algebra. So what we're going to do, just to alleviate things, is if I'm doing a change in position with respect to time, when I start dealing with my trigonometry identities, I'm going to end up with a position, angular frequency, times the sine of the omega t. That's how my velocity is going to be described. So if I go back here, let's kind of look at what's happening physically. So this is my thing that's bouncing up and down, right? Where on this curve is the velocity 0?
At the bottom of the loop?
It's 0 there. It's also 0 at the top, right? Because it's going to behave just like that ball. If I'm tossing that ball up into the air, when it changes direction, at that instant, the velocity is 0. Okay? That instant, the velocity is 0. Similarly, the velocity at the bottom is changing direction, and the velocity is also 0. So I'm going to have it be 0. Where on this graph is it going to be traveling the fastest? Where's its maximum velocity going to be? Well, it's not. Well, at the end, sort of, just because that's where I drew it. It's when it's going through the midpoint, right? When it's going through the midpoint. So let's look at that for a second. So if I look at the potential energy of the spring, right? We know what the potential energy of the spring is. Potential energy of the spring is kx squared. But if I'm thinking about this as a mass system, okay, so it's bouncing up and down. So here it's at the top, here is at the bottom. The potential energy there is the maximum, right? Potential energy at the bottom is also the maximum because we have a restoring force. But if this is at the maximum, it's where my potential energy is, and my kinetic energy, which we know is 1/2 mv squared, right? So if my potential energy at the spring and my kinetic energy at the spring, if this is where the velocity is equal to 0, this is where the velocity is maximum. And this is also where the velocity is equal to 0. So as I'm going through this loop, not only am I seeing a change with respect to position, I'm also getting a change constantly between potential and kinetic energy throughout the system. I'm going to have 0 potential energy here, I'm going to have 0 potential energy there, I'm going to have the maximum kinetic energy in the middle, but I have 0 potential energy in the middle. So I can look at this system in terms of energy as well as in terms of motion. I can look at that system in terms of energy as well as in terms of motion. We also know that acceleration due to time is going to be a change in velocity with respect to time. And again, I can go through all the gory details, but for you guys, we're just going to go ahead and say it's a omega squared cosine omega t is related to the acceleration. Okay, it's related to the acceleration. So let's actually look at the acceleration because we can. Okay, we can actually look at the acceleration because we can. I'm going to switch back to the graph here. Oh, I already have it open. Okay, I'm going to reset. Okay, I'm going to reset. I'm going to get rid of the wheel. I'm going to use the accelerometer. We're actually going to look at acceleration and force. Actually, we'll just look at acceleration. And I'm going to bounce the system just like I was bouncing it before. So for those of you, because I can't do dual screens, which is a pain in the tushy. But I'm just going to I'm going to bounce it up and down and do the acceleration so we can actually see acceleration. Oops, on the wrong one. Had the wrong sensor going. So there's my acceleration, it's bouncing up and down. I put some energy into the system, so I'm going to stop. I'm going to get rid of the X and the Z because we're really just worried about the Y. And I'm going to go in here and we're going to look at it from 6 to 10 seconds. But we also don't have it zeroed, but that's all right. But you can tell where I'm going to have my acceleration be its maximum and its minimum. You can tell where the acceleration is going to be 0. And you can see that it's going to behave just like a sine wave, just like what we had before. And so I can give you, if I give you the position versus time graph, or position versus time function, you can quickly give me the acceleration versus time function, and you can give me the velocity versus time function. And we can use conservation of energy in the system. We can use that potential energy and kinetic energy in the system. And remember, because we showed it just a little while ago, there we go, that K actually is related to physical property, or not K, omega. I'm getting ahead of myself. Omega is related to a physical property, K over M. And I'll show you where that comes from. So let's start here. We'll start with force is equal to mass times acceleration, which is equal to minus kx for our bouncing system. Okay? For our bouncing system. So I'm going to solve for acceleration. Acceleration is equal to minus K M X okay. Now I'm going to write out my acceleration that we just showed was A omega squared, there's a minus, cosine omega t. And I have a minus kx, except now I'm going to plug in my A cosine omega t for that system. Cosine omega t cancels cosine omega t. Oops, A cancels as well. I get minus omega squared is equal to minus kx. Oops, that's not an x, that's an m. Sorry. It's an m. That cancels. Omega squared is equal to k over m. Omega is equal to the square root of k over m. Okay, ready to do some sample problems now. And again, folks, if you haven't gotten on the website, please do so before noon so we can make sure you get help to get there. Because you'll want to be able to get started on the homework to get your extra credit and all that good stuff. All right, so we have a satellite. That has a period of 90 minutes. We're just going to determine the frequency of the satellite. So we're just going to determine the frequency initially. So one cycle is equal to 2 pi. Okay? And if the period is 90 minutes, we're going to need that in seconds. And so if we do that conversion, we get 5,400 seconds. Okay? So if I do this, that's my period, it's 5,400 seconds. And so the frequency is 1 over the period, which is going to be equal to 1 or 0.00185 hertz. We can determine the angular frequency. That's just 2 pi times frequency. And so that equals to be 1 or 0.00116 hertz. And if I want to find the amplitude, okay, I want to find the amplitude, I can go back to Kepler's equation and show that the period is 4 pi squared universal gravitational constant, mass of the Earth, is my nominally equal to my radius cubed. That is my amplitude that I'm looking for. I want to find that amplitude. G, just to remind everybody, since it's been a while, is 6.67 times 10 to the minus 11 Newton meters squared kilograms squared. Mass of the Earth, where you get that is inside the cover of your text, 5.98 times 10 to the 24 kilograms. So if I plug in 4 pi squared, gravity, mass of the Earth, the amplitude actually ends up being 6.65 times 10 to the 6th. And that's in meters. And if I have all of that, if I have the amplitude and I have omega, and I have a question over there, or is it just I'm hearing somebody outside the... Okay. Alright. So now, if I have amplitude and omega, I can tell you the position of that satellite with respect to time is going to be 6.65 times 10 to the 6th meters cosine 0.00116 times time, and I can give you its position, so that's its position at any given time. So we can actually write the equation. All right, we'll do one more and then we'll call it a day. This time I'm going to use a car example. Okay, so inside the cylinder of my car I have a piston. Okay? And we're going to define the piston's position with respect. So it's going to be 6, and this is a big piston, so this isn't, so it's 6 centimeters cosine, and we're going to use 3t plus pi over 2. T is in seconds, and that's the units. So if I were just write this out, I'm going to get 6 cosine 3t plus pi over 2. So the position of my piston is given by that. So first thing I want to do is I want to find the position at t is equal to 3 seconds. Well, that's easy enough. I'm just going to find y, 6 cosine 3 times 3 plus pi over 2. Plug that into the calculator, and I'm going to end up with minus 6 centimeters, I think. I'll double check that. I'm going to plug it in. I'm not 100% sure, so we get. So inside the cosine, and you've got to be in radians this time, folks, so you've got to make sure you're in radians. So I've got 9 plus pi divided by 2. So this ends up being cosine inside there is 0.10.6. So I get 6 cosine 10.6. No, I knew that one didn't look right. So it's minus 2.3 centimeters. So that's the position at t is equal to 3 seconds. If I want to find the amplitude, what's the amplitude? Yep, 6 centimeters. Okay, if I want to find the frequency,
over 3.
well, that's close. Omega is equal to 3. Okay, omega is equal to 3, which is 2 pi times the frequency. And that's common, okay, folks? That's a common mistake. And when you're working on your homework, double check that, be careful. Because we're so used to just plucking the data right out of there, we want to make sure that we're catching that. So that's okay, because frequency is going to be omega divided by 2 pi. And so that's going to be 3 divided by 2 pi. So that's going to give me weird frequency. Okay. Now, the other thing about that is you can go ahead, depending on how WebAssign wants you to do the answer, you can go ahead and calculate it out in terms of its digital, or you may just want to leave it in terms of pi, depending on what part of the problem you're in. You may just want to leave it in terms of pi. It's just whatever's going to work best for you.
I'm having a hard time seeing. Did you erase part of it? Oh, okay.
For some reason, it kind of faded toward the bottom
Yeah,
of the screen.
it's reflecting the light. Some certain positions it reflects the light. Just holler at me and it'll shift it up. Then, if I want to find the equation for velocity, okay, so I want to find the equation for velocity, so my position is 6 cosine 3t plus pi over 2. We know that velocity is going to be a omega minus a omega sine omega t plus my phase angle. So now that's going to be minus 6. My omega is 3 sine 3 t plus pi over 2. So you're just picking the data out to get the next one. So now I can write down the acceleration. Acceleration is minus a omega squared cosine omega t plus the phase angle. So now that's going to be minus 6, 3 squared cosine 3t plus pi over 2. So for your quiz next Friday, things you're going to have to remember. Omega is equal to 2 pi times the frequency. Frequency is 1 over the period. X is going to be a cosine omega t plus my phase angle. V is going to be minus a omega sine omega t plus the phase angle. And A is going to be minus a omega squared cosine omega t plus the phase angle. You're going to need to be able to write the equation. So if I give you this, write the equation. And be able to pick out A, omega, T, F, phase angles. That's all the quiz is going to be over. So that's the stuff right there. I'm going to scroll out here just a little bit. Oh, that's as much as I can scroll out. Because I'm not going to allow you to have notes, cheat sheet, or anything like that. That's what you're going to have to remember. Yeah,
How do you pick a phase angle out of the graph?
it's where you start.
Oh.
Okay, it's where you start. So since this is cosine omega t, and I started at 0 here, so for cosine, so that's actually a great question. So cosine omega t plus my phase angle has to equal 0. Well, if I'm at t is equal to 0, it's when the cosine of my phase angle is equal to 0, and that should be 90 degrees. Because I started at 0 at that point. But if it's not 0, say it's like 0.5, then you can figure out your phase angle from that. So that's a great question. Great question. Questions over there? All right, guys. You good? We'll see you Wednesday.